Hey, and welcome to our video about phase diagrams. So phase diagrams are essentially a map of the most stable phase of a substance. And there's lots of different kinds of phase diagrams, but the kinds that we will look at, the map will be two-dimensional and it will be with respect to pressure and temperature. So what this means is that we've got one axis where we've got the pressure of the substance, and we've got another axis that represents the temperature of the substance, and then we're going to draw a map. So essentially we're going to have a series of lines that lay out the regions where you're more likely to have yourself a solid. So we're going to find that a solid is often found in this region here, where you've got sort of high pressure and low temperature. And down at the bottom of the diagram, where you've got low pressure and high temperature, it'll often be a gas. And in the intermediate region, you've got a liquid region, where you've got pressures that aren't too high and temperatures that aren't too high. And these lines here represent these boundaries. And so if you're on the boundary, then both phases, or in the case right here, all three phases will be equally stable. But as soon as you step into one side or the other of the line, you're looking at the most stable phase of the substance. So let's go ahead and sketch water's phase diagram. So we're going to put pressure here on this vertical axis, and we're going to put temperature here on this horizontal axis. And so the phase boundaries I'll draw in yellow. And water is actually kind of neat, actually, because there is a solid phase here, a gas phase here, and a liquid phase here. And the boundary between the solid and the liquid phase almost always actually slopes upwards to the right. But in the case of water, it's actually weird. It actually slopes up and to the left. And we'll see that this is true for a lot of substances that have a solid density that is smaller than their liquid density. So most solids are actually more dense than the liquids. That means that when you freeze a substance, then the solid will sink in the liquid. But water is kind of weird, and we all know that ice floats on top of water, and we'll see that that difference in density actually gives rise to that negative line. And if you take a class like physical chemistry, we'll actually go ahead and calculate the slope of the line, and we'll show that when the densities of the solid are smaller than that of the liquid, then it will have a negative slope. And we're going to go ahead and draw the other phase boundary here between the liquid and the gas, and it looks something like this. There's actually a point here where all three phases are in coexistence, and for a simple substance, then it'll always have at least one of these points here. This is called the triple point. And the triple point has a characteristic temperature we'll call T3, and a characteristic pressure we'll call P3. 3 there is standing for the fact there's three phases that are equally stable at this point. And I think for water, T3 is something like 0.01 degrees C. What's kind of neat, actually, is if you look at water, there is only one temperature in the entire universe where water will exist in all three solid, liquid, and gas phases. So you can almost develop a temperature scale based on this idea. And the triple point pressure, I think, is 4.6 torr, or 4.6 millimeters of mercury. So it's a very low pressure, but again, there's only one pressure in the universe where water has all three of those phases equally stable, and that exists at 4.6 millimeters of mercury and 0.01 degrees Celsius. Why don't we extend the liquid gas line anymore, where it turns out that there is a point here that we call the supercritical point. So let me write that down. So supercritical point, and sometimes we represent this as PC and TC, and it turns out that above this point here, there is no distinction between the liquid and the gas phase, literally the boundary between them. So, you know, if you pour some water into a glass, then you've got water in the glass, the liquid, and above it you've got water vapor. Well, beyond the supercritical point, the difference between the liquid and the gas suddenly ceases to exist. And so we have what we call a supercritical fluid in this region here. So the lines between the solid and the gas and the liquid and the gas correspond to the vapor pressure above the solid and the vapor pressure above the liquid, respectively. So those lines are actually fairly easy to measure. And we have essentially both phases in equilibrium. So at this point here, we've got a line, or if you're on the line, then both the solid and the gas are in equilibrium. And so the vapor pressure is the pressure where you've got the equilibrium between the gas and the solid. And likewise, over here, you've got the equilibrium between the liquid and the gas. And so if you measure the vapor pressure, essentially you're mapping out this region here. This line up here at the top is the sort of the boundary between between the solid and the liquid. So this essentially corresponds to the normal, or actually I should say just the melting point of the substance. So here's how we're going to go ahead and deal with this information. So I'm going to go ahead and flip to a new slide, and I'm going to draw this diagram here in naked form, and we'll kind of use it to map out the temperatures and the pressures where things melt and boil, and we'll see all sorts of really neat information we can get from this.